Hello, welcome to your lesson on infinite geometric series. Let's begin with a little bit of a flashback. Looking back on geometric sequences, we looked at two main types. One was called a diverging sequence, for example here, and another type was called a converging sequence, for example here. In a diverging sequence, the R value, or common multiplier, is greater than 1. And we can see here the numbers as a result, the terms in the sequence grow in value. In this case, the R value is greater than 1, or also we can say it's greater than -1. It can be a negative multiplier, but greater than -1. Converging sequences, contrary to that, they have terms that decrease in size. So in this case, we can see the R value is -0.5. When the R value is less than 1 like that, or between -1 and 1, the terms get smaller and smaller. That's called a converging sequence. So again, the R value is between -1 and 1. Okay, we also did a little bit of investigation, and we looked at an arithmetic sequence with U1, 3, and common difference of 2. So you can see it went up by 2, up by 2, up by 2, up by 2. There's our simple arithmetic sequence. Finding the sum, we have the sum here. So after one term, the sum is 3. After two terms, those two add up to 8. After three terms, we have 15 as the sum of those. So here's all the sums. Now let's plot the sums. The sums graphed will look like this, and you can see in this case we have an arithmetic sequence always growing by 2, and the sums as a result have a little bit of a curve to them. So they are growing, 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 and the sums will continue to grow, never reaching a certain number because they will just continue to grow forever. Let's look at another arithmetic sequence. This one, we had a common difference of 0.5, so you can see U1 here, up 0.5, up 0.5, and so on and so on. It's going up by a small amount, but still the sum keeps rising by bigger and bigger amounts, because even though the common difference is a small amount, the sum ends up growing by more and more. So let's look at the sum when we graph that one. Here's the first sum, here's the sum after 2 terms, here's the sum after 3 terms, and so on. You can see it looks almost linear, but it's not, because look, this goes up by 4.5, this goes up by 5.5, then this goes up by 5.5 again. No, is that right? Let's see. And then this goes up by, that went up by 6. This went up by 6.5. So it goes up by a little bit more every time. So the sum is rising. Again, there's a slight curve to it, and therefore the sum is never quite reaching a certain value because the sum will just continue to grow. We also looked at a geometric sequence where the first term is 1 and the common ratio or multiplier is 2. So 1 times 2 is 2. And then 2 times 2 is 4, and 4 times 2 is 8. So you can see, always multiply by 2. In this case, the terms are rising very quickly in value, and the sum as a result will also grow quickly. We have a sum of 3 after 2 terms, and then if you add up the first 3 terms, the sum is 7, and the first 4 terms, the sum is 15, and so on. Plotting the sum, we can see it's going to start slow but then rise very quickly, because again these terms grow, therefore the sum is going to grow even more. So definitely that is rising very quickly, and again the sum does not approach a certain value, it's just going to keep rising forever. Finally, we had a geometric sequence where the first term was 1 and the common ratio was 0.5. So we multiply by 0.5, we get this. Multiply that by 0.5, we get this. Multiply that by 0.5, that. On and on and on. So since the multiplier is now less than 1, the terms in the sequence are decreasing. Therefore, the sum of terms, you'll have, look, these two add up to 1.5, but then you add that, you get 1.75. Then you add that, you get that. So yes, the sum is increasing, but since the terms are getting smaller and smaller, the sum is increasing by a smaller amount every time as well. So eventually the sum kind of reaches a plateau. Let's take a look at that when we plot it. So here's the sum after 1, here's the sum after 2 terms, sum, and on and on. And like I said, the sum is reaching kind of a plateau. That plateau is very important because it basically is reaching a limit, or what we also call an asymptote. So the sum will eventually reach a limit, though. You'll be adding such tiny pieces eventually that they won't really matter. They will be so tiny they will not matter, and we can say the sum actually reaches a certain value. So this brings us to a big idea. Let's take a look. We have some geometric series here, and how are they different from one another? Well, look at the first one. The first one has an R value of 3. We can see it's multiplying by 3 every time. We can also see in the second one the r value is 4, so also multiplying by 4 every time. But in the last one we have an r value of 1 over 10. It's 1/10. 1/10. Every value is 1/10 of the previous. Let's take a look. In the first one, it is a finite sequence because it has a final value here, a final term, and it is diverging. You can see these numbers are getting bigger, 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 so it's diverging. We were talking about that. In the second one, it's an infinite sequence because we see this dot, 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 and it is diverging as well. These values are getting bigger and bigger and bigger. The last one, however, is infinite and converging because the values are getting smaller. And that last one is like that last one we saw in the investigation, where since the values are getting smaller, eventually the sum of the values will also reach kind of a certain peak. Let's see what we got. So we're talking about infinity here. Let's move on with our discussion. So the first one, or the question is, can you find a sum of any of these? Well, based on the discussion we've had so far, we can say, yes, the third one we can find a sum for it. Because again, we'll be adding such small values eventually that they won't really change the sum that much. So we can say there is a sum to this infinite one, but only when it's converging. So let's take a look. Here's a geometric sequence. R value is 4, multiplying by 4. Here we have another geometric sequence. R value is a half. We're multiplying by a half. So in the first one, written as a series, we're going to say the sum of terms. So the sum, and here written as a series, we also have the sum of the terms. Now, the sum of one term is 2 because it's just 1. The sum of two terms is going to be 2 plus 8, 10. The sum of three terms is going to be 2 plus 8 plus 32, 42, and then the sum of four terms is that. Over here, let's look at the sum. The sum is 40 after one term, and then after two terms it's going to be 40 plus 20 is 60, and then 70, and then 75. So again, this sum is growing quickly, whereas this sum is growing, but growing at a smaller speed or smaller rate eventually. So that brings us to the graphs. Here's the sums graphed for the, sorry, is that right? Yeah, here's the sum after 1, sum after 2, sum after 3. So here's the sum for that divergent sequence, and the sums you can see are growing. And then the sums for the other one, hold on. So we have the sum then to infinity, right? If this is sum of 1, 2, sum of 3 terms, the sum to infinity is, well, it's like infinity, right? If you keep going here and you keep adding terms and they keep growing, the sum, if you go to infinity, will be infinity. And that's divergent. Let's look at the other one where we had these terms here. The sum after one term is 40. The sum after two terms is 60. The sum after three terms is 70. And we can see that here. Here's the sum after 1, after 2, after 3 terms. And you can see here the sum is going to reach that plateau that we talked about, an asymptote, a limit. The sum has a limit because eventually the number you're adding, see these are decreasing, will be so small that the sum itself won't change very much and it's reaching some kind of limit. So this is a really important idea in sequences. We have that asymptote, and the sum to infinity in this case we'll say is 80. We can see it's reaching a limit at 80, and we'll look at how to calculate that in just a second. So to summarize, in a convergent sequence, there is a sum. We say there is a sum to infinity. There is a sum because it's going to get so it's going to reach that value and not change much. But in a divergent sequence, there is no sum. The sum is infinity because the terms will keep increasing, and therefore the sum will keep increasing. Okay, let's summarize that with this formula. So well, maybe I'll come back to this in a little bit. Let me just jump ahead. So there's a formula, and the formula is this. Where sum to infinity for an infinite geometric sequence or series is this. That formula looks very familiar. It looks very similar to our sum formula for geometric series, but it's a little bit different, a little simpler, and we'll look at the proof for that later. But right now, there's a formula. Let's add that to our notes page. And know that this only works when the r values are less than 1, or absolute value is less than 1. In other words, the r values are between -1 and 1, because those r values will create a convergent sequence, right? R values are less than 1. When you multiply by a value less than 1, the terms will get smaller, smaller. It's convergent, therefore there is a sum. Okay, let's apply the formula. So here's the first problem. Give it a try. So let's check our work. U1 is 1.5, and the r value is 0.75 because each time it bounces, the height it reaches is 0.7 or 75% of the previous one, so that's the multiplier. We're looking for the sum to infinity. The formula is this. So we just put those values in. It's that simple. So the sum to infinity here will be 6. So the distance traveled by this ball will be 6 if it bounces to infinity. However, this 0.75 only represents the bounce, how high it bounces after, right? So the first, you could say it started at 1, and then it bounced, and then it got to 0.75, and then it bounced, and it got to 0.75 of that, and so on. So this sum here is only showing the sum of like the one branch, right? Like the initial height, 1, and then, or you can say the fall, and then the next fall of 0.75, and then the next fall, and the next fall. So this sum is not giving you these upper bounce parts here, right, also, right? So we need to basically, if we're going to answer the question of how long is the distance traveled, we need to multiply our sum by 2, because there's an up portion and a down portion. So basically, everything we get in this sequence has to be doubled, because there's up and down, up and down. All right, so total distance is 12, but we subtracted the 1.5 because of the original 1.5. Again, if we doubled that, we would have to have a initial bounce up to there, but it was dropped from that height. So these are all doubled, see, because they all have two sides. But this first one, the initial fall, is only one-sided. It's not two-sided. So we subtract that 1.5. It's a little bit tricky there. It required a little logic, but I hope you figured that out. Okay, here's some more. For each of these, decide if it's an infinite geometric series. Sorry, they all are infinite geometric, but is it converging? And if it is converging, then find the sum. Okay, first one, definitely converging. We can find the r value by doing one term divided by the previous term, and now we see the r value is a half. Since the r value is less than 1, it's converging. Use the formula, you get the sum. Next one. This time when you calculate the r value, 2/3 divided by 1/3 is 2. Therefore, r value is greater than 1, so it's going to be diverging. Therefore, no sum. Next one, r value is negative a half. That is a value that's between -1 and 1, so it is converging. Use the formula, you get this sum here. Final one, we see the sequence here. From there, we can see u1. You can find u1 by plugging in 1 in there. You can find u2 by substituting a 2 in there. Now we have u1 and u2. Divide those two, get the r value of -1/3, and we can see it here also. And then that tells you it's converging, and then you can find the sum using the formula. So I hope that practice helped you figure out how this works and when you can use the formula. Now let's go on to this one. We have an arithmetic series. This is now a mixed problem set, so it's not just these infinite geometric, but we're going to look back at all the sums we've looked at. So back to arithmetic series, we're given a sum, we're given a u1, we're given a un term, we don't know which term that is, and it says find the value of n. So in other words, how far into the sequence is this? Given the sum, so let's see if you can figure this out. Okay, so we're using the sum formula for arithmetic. Plug in what you know here. That allows you to solve for n. N is 12. Is that all we have to do in that one? Yeah, I think that's it. That was pretty simple. It turns out that was pretty simple. Okay. All right, next one. How about this one? The second term of arithmetic sequence is this. And the sum of the first 4 terms is this. Find the first term and the common difference. Okay, u2 is this. The sum is this. We can say this using the u2. We put it into the un formula. Allows us to solve for this formula. But there we have 2 variables. Therefore, we're going to take the sum formula for the first 4 terms. All right. Solve that, simplify until we can substitute. I think this 7 minus d that we got for u1 here was substituted right here, and then you solve through there and get a d value, and that allows you to solve for u1. That was a little trickier, but that's the kind of problem you should be able to solve at this point using all the formulas we've looked at. Let's look at this one. Okay, check your work here. This one's also tricky. Okay, that one we can talk about in class next time, but you're going to use a polysimult. It's an app on your calculator, but when you end up with an equation like this, it's tough to solve. So let's stop there in that one, and then I'll show you how to do that next time. Here's another. And check your work there. And this one. Check your work here. Okay, those are tricky, but you can do it. Look back on those if you need to. Pause the video. They're tough.